Hey friends, it's good to be back with you. Today it's time to learn how to solve differential equations using Laplace transforms. Now Laplace transforms are just another in a family of integral transforms that I mentioned earlier. Now by far, the two integral transforms you'll see most often are Fourier transforms and Laplace transforms. They get used for different things. They're going to occupy kind of different places in your life. The Fourier transform is almost always used to transform some measured data, or sometimes a function, from mostly time domain, once in a while spatial domain, to a frequency domain. Because oftentimes we want to see what frequencies are present in data, and it's not apparent in time domain. Now, if you've ever played an instrument, you know a little bit about this. Hang on a second. This is a little mandolin. These things are handy to have in the office. I'm kind of slowly learning how to play this thing. And this little gizmo right here is a tuner. I clip it onto the end and it listens to the vibrations in the headstock right there. And I can pluck a string and it'll tell me what frequency I'm making, whether I'm in tune or not. And so I can adjust the tension of these little tuning pegs here and tune the thing up. This little thing has 8 strings on it, so you've definitely got to tune it before you play it. In fact, I think I told you a friend suggested to me that mandolin is Italian for out of tune. So that's frequency domain, and you usually get to frequency domain using a Fourier transform. Most often you'll see it expressed as FFT for fast Fourier transform, and FFTs are everywhere. Now a Laplace transform is this right here. It's awfully close to a Fourier transform, and it has that same form that integral transforms have. There's the time domain function, and there's this kernel function right here. This is kernel like a kernel of corn, not like an army kernel. And e to the minus st, where s is sigma plus I omega. Now this is usually called a damping term. If sigma is 0, what you get is a Fourier transform. If that goes away, s equals I omega, this becomes pretty close to a Fourier transform. The integration limits are different. If you plot the real part of the kernel function, it's a decaying sine wave. What it looks like is a sinusoidal function whose amplitude goes down as e to the minus at. Great, so far. So why do we care about this? Well, we're very seldom going to actually evaluate this for functions. We'll most often use tabulated or canned expressions for these, although you can generate them yourself if you need to. And it isn't clear from here why we're going to use this to solve differential equations. It's very rare to see data expressed in S domain in a plot. So it's not like the Fourier transform in that sense. The Laplace transform has some unique characteristics that allow us to solve differential equations more easily. And this is how we're going to do it. Without this framework, none of the rest of this is going to make any sense. So here's what we're going to do. We're going to start with an original problem in time domain. Well, I don't know about you, I live in time domain. I don't know how to live anywhere else. So if you look at the differential equations that describe physical law, quite often they're written as differential equations in time domain. Newton's laws, for instance. Okay, so we're going to start with a differential equation in time domain. Now, why don't we just solve it there? That's the obvious thing to do. You know, go through some mathematical process and find a function, y of t, that solves the differential equation, and we're done. Well, it's often very hard to do that. It's easier, sometimes this is the difference between a solvable and an insolvable problem. We're going to start in time domain, and we're going to transform it into S domain. How do you transform it? That's what this is for. And again, most of the time here, we're going to use tabulated functions. Well, in S domain, you get the same information, the same function, it's just in a different form. And that different form is easier to solve. So we solve it in the S domain. Well, what does it mean to solve it? Well, if there's a differential equation where the independent variable is t and the dependent variable is y, so you have maybe y prime equals something, or dy dt equals something. What you're trying to do is you're trying to find some function of y of t that makes that equation true. Well, it's hard to do here. We're going to transform it into S domain, and we're going to find a function y of s that's easier to find. Once we find y of s, we're going to transform it back into the time domain. So problem we don't know how to solve, problem we do know how to solve, transform it back to where it needs to be, now we're good to go. All right, so along with the Laplace transform, there are, of course, inverse transforms. So this is the big idea. Now, let's talk a little bit about how this works. Now, I'm going to have to erase my board here, so give me a second. The thing that makes a Laplace transform so handy for solving differential equations is what happens when you do the Laplace transform of a derivative. Here's what it looks like. So if I say capital L of y prime, that's not a very good L, there we go. That means Laplace transform of the derivative of a function. What I get is S times the Laplace transform of the function only minus, make sure I get this right here, y sub 0. That means if you want, in Laplace domain, if you want to take a derivative, you just multiply by S. So a derivative in time domain becomes a multiplication in S domain. And right there is your initial condition. The initial condition's already baked into it. Well, that seems handy, doesn't it? Well, what happens if we take the Laplace transform of a second derivative, double prime? Well, this is what it looks like. S squared, just what you'd think, Laplace transform of the original function minus S times F, I'm sorry, I'm doing it again here. Hang on, let me get out of your way here. So, with the second derivative, you're going to need two initial conditions because you've got a second order derivative. Well, there's one of them, there's the other one, already baked in. So, if initial values are already part of the transform, stands to reason that this would be a good way to solve initial value problems. Let's try it. Okay, so the first thing we're going to need is a differential equation. Got one right here, and I can't remember where I found this. This is from Wikipedia or a textbook or something. If you're poking around, you may find this on your own. Now, since it's second order differential equation, we need two initial conditions. So y of 0 equals minus 1 and y prime of 0 equals 1. So we got ready to go there. Now, first thing we're going to do is transform this into S domain using the Laplace transform. Now we're going to need a way to distinguish between y in the time domain and y in the S domain. So right here, this is anywhere you see this lowercase y here, that's actually y of t. It's pretty typical to just write it down that way, but you got to remember, this is a differential equation. Y is a function. In order to solve this, what you're doing is you're trying to find y of t that satisfies this equation. So in S domain, I need some other letter, I guess. So I'm going to use an uppercase y that looks like that. And that's going to be Laplace of y. I guess if we put the t in there. There we go. That's what's going on here. So when you see this is an uppercase y. That's in Laplace domain. Lowercase, that's in time domain. Good to go? All right, so first thing I'm going to do is let's just transform this into Laplace domain. So this is going to be S squared. All right, so that's just y double prime. That's the Laplace transform of y double prime, just like we've seen before. So let's keep going here. All right, there's 2. There's the transform of y prime. And then we're just going to add in y in the S domain. This is y in the time domain, that's y in the S domain. So it's just one-to-one correspondence there. And the last thing I need is, what's that in the Laplace domain? Well, it turns out it's pretty straightforward in the Laplace domain. 1 over S plus 1. So that's it. All right, so let's make sure we know what we're about to do here. We've got all this stuff written out on the board. Now, I'm going to use just basic algebra to clean all this up and get what I hope is a neat expression in the S domain. Now, I want it neat because I need to be able to transform it or inverse transform it back into time. So, next step here, let's do a bunch of algebra and see if we can clean this up. Now, before we dive into the details, let's make sure we understand what we're trying to do here. I'm going to work on this until I get y sub s equals something, some expression of s. When I inverse transform the left side, y of s becomes y of t, and when I inverse transform the right side, that becomes some function of t, and that's the solution to the original differential equation in time domain. So let's start by working all this out. It's going to take me a couple of boards here probably, but we're going to get y of s equals 1 on one side of the equation equals some expression of s on the other side. So here we go. Now, that's, we already know, that's minus 1, and that's 1, and let's see, that's minus 1. All right, so let's start writing all this out. S squared y, okay, there. First step. Now let's start gathering terms here. Okay, so s squared 2s plus 1. So I took care of that one, I took care of that one, I took care of that one. And let's keep going. Okay, there's the next step. So let's take the next step here. Let's write all this out, start gathering some terms here. Got room here? I have enough room. Okay, here we go. There's the next step. Now what I'm going to do here is I'm just going to erase this and keep going. But what I want you to understand here is all I'm doing, I've substituted in the expressions for y double prime and y prime. Y just showed up right there again. And all I'm doing is just sort of gathering terms. This, from basically here on down. This is 8th, maybe 9th grade algebra. All right, so let's make some more room, keep going. Okay, so far so good. Let's push the s plus 1 over there, and I'm going to factor that. That's s plus 1 squared. All right, I'll get rid of that now. Okay, next step. You can see where I'm going next. I'm trying to get y on the left side of the equal sign and everything else, all the s's on the right side of the equal sign. So all I got to do now is divide by s plus 1 squared. All right, nice and tidy. But now what? This is still in Laplace domain here. This is still in S domain. Well, now what do? Well, I do an inverse Laplace transform. The inverse Laplace transform is also an integral transform. But since these are so simple, we're going to be able to write these out using just tabulated transforms. You can go in any calculus book or Wikipedia or wherever you want, and you can find the inverse transforms of these. So let's erase this, and I'm going to write out the inverse transforms. Okay, now notationally, that L to the minus 1, that you're not actually inverting L. This is notation for this is the inverse transform. 1/2 t squared e to the minus t. There's 1. And there's the other one. All right, it's getting easier, isn't it? Well, just to make sure we know, the inverse transform of y sub s is y, oops, not capital anymore, it's yt, right? We know that's this, so 1/2, okay, just last little bit of algebra here. There we go. After all that, that's the solution to the differential equation. Now this is a true solution too. This is a closed form expression for y sub t. If I were to plug y sub t back into the original equation, the original differential equation, that would solve it. I would get the left side equal to the right side. This is different than the numerical solutions we've done earlier, because this is truly a closed form solution. This is the equation that solves that differential equation. When you do a numerical solution, you don't know what this is. you're drawing a picture of it. So I can draw a picture of the equation without actually knowing what the equation is. Well, with that in hand, let's check it. There's two ways I know to check it. The first one is to substitute that back into the original differential equation and see if it solves it. And the second one is let's compare an exact analytical solution with a numerical one. Okay, the first way to check our answer is to substitute the exact expression we found using the Laplace transform method back into the original differential equation. And just to remind you, here's the original differential equation we're trying to solve. Now I'm doing this in MathCAD Prime because it's a little easier to read than MATLAB, but this also works in MATLAB. So there it is. I typed this in earlier. There's our exact expression we found on the board. Well, if I do this right, let's see if I say y. And let's see, I'm going to go and pick the differential operator here if I can find it. I needed to pick it twice. T plus 2 times y prime of t plus y of t. There, what's that? If I do this right, that should equal e to the minus t. Well, it doesn't look too good, but wait, let's simplify this. And there it is, e to the minus t. So it clearly worked. Now there's another way to do this in MathCAD. I can set this up so I can actually put the full differential equation in here. Now I can ask MathCAD to simplify this, and if the left side really is equal to the right side, it should equal 1. And there it is. Now the other way to do this is to solve the original differential equation numerically and compare it to the analytical solution. All right, so let's clean up the workspace here. I'm going to move this up here, and I'm also going to rename this. I'm going to call this y sub exact to distinguish it from the numerical result we're going to get. And in MathCAD, we're going to do this using a solve block. This isn't the most convenient format in the world, but this is the one they use for solving differential equations. Anyway, it works fine. So for constraints, I just type in the differential equation and the initial conditions. All right, I've got the constraints typed in. I think I'm able to shrink this down a little. Yeah, like I said, this is not the best formatting in the world, but this is what we're stuck with. And the function in MathCAD that solves differential equations, well, one of them, is called ODE solve. So all I have to do now is this. And I need to give it a time range. So let's go from 0 to 5. There it is. So I've got it solved. Let's see. Let's go ahead now. Maybe I can move this up here. There we go. Let's go ahead and plot the two of them. And we'll go from horizontal axis goes from 0 to 5. There we go. That looks right. So let's add another trace here. It's hard to say if I've actually got two on there. Let's do this. Let's make the trace color red, and let's put some symbols on there. So you can kind of see I really do have two traces, and they really are identical. There you can see the red over the blue. And if I turn on the symbols, the line looks like it's really getting dark. Well, it's not dark, it's just that there's just so many symbols smashed together. It looks like the line is wider. So I've shown it two different ways. Now if you want to see this another way, let's go ahead and remove that trace. Let's put this here, and let's make a duplicate of it. Let's see, right there. Instead of y exact, let's just make it y. And you can see those are identical. The two are the same. Let me line them up here so make it a little easier. There we go. So it's obvious we have the same answer on both of them. So we've proved this two different ways now. We've compared the analytical solution, y exact, to the numerical solution. And earlier, we showed that if you plug the analytical solution back into the differential equation, the equation is satisfied. So just to reiterate, the thing that makes all this work is the properties of the Laplace transform. Taking a derivative in the original domain, usually time or space, usually time I guess, is equivalent to multiplying by s in the Laplace domain. And this property of Laplace transforms allows us to take a function in, say, time domain that we don't know how to solve, transform it into Laplace domain, solve for y of s, and then inverse transform that solution back into the time domain to get y of t, which is the solution to the original differential equation. So once you see the structure, it's actually pretty straightforward, and all you need is a list of Laplace transforms or the ability to work them out using some software. Well, there are lists of Laplace transforms in most calculus books and all over the web. And you can also use the Laplace functions in MathCAD or MATLAB to find Laplace transforms when you need them. So I hope this helps, and we'll talk to you next time.